Good morning, everyone. I am Lakshman Kesi, a graduate student at the University of South Carolina. The topic of my presentation today is surface damage imaging for input to load rating of bridges. This is the outline of the presentation. In the introduction, I'll talk about the present condition of bridges in South Carolina, the need of load rating, and the use of surface damage imaging for input to load rating of bridges. I'll explain the objectives. The methodology and results of the study will be explained, followed by the conclusions and future works. Introduction. The state of South Carolina has more than 9,000 bridges in its inventory. Most of these bridges are precast, reinforced concrete slab bridges. More than 90% of these bridges are managed by South Carolina Department of Transportation, SCDOT. These bridges have been subjected to decades of service deterioration. The average age of 40 years is very close to the service life of 50 years. Moreover, more than 30% of the bridges were designed for yacht 10 or yacht 15 truckloads, which is significantly lower than the current standards. These slabs are subjected to heavier trucks. The heavier trucks can reduce the life of the bridge, and the heavier trucks can cause permanent structural damage. So, the SCDOT has prioritized the evaluation of these bridges by load rating to determine the safe load carrying capacity and to ensure public safety on these bridges. Load rating is usually done to determine the safe load carrying capacity of the bridge. To maintain the safe use of the bridge, load postings are done, which is based on load rating. The need of bridge strengthening and the decision to make the decision for overweight vehicle permits are made based on the load rating. The load rating is based on the existing conditions of the structure, material properties, loads, and the traffic conditions at the bridge site. So it is assumed that inspections are carried out at regular intervals to get the present conditions of the bridge. The manual for bridge evaluation has given 3 analytical methods for load rating: load and resistance factor rating, load factor rating, and allowable stress rating. In order to carry out the load rating of these bridges, the capacity has to be calculated. The capacity depends on the material properties and the structural layout in the present condition. So the inspections has to be carried out to find the defects that can reduce the critical strength of the bridge. Cracking is one of the deterioration which is the earliest sign of distress in the bridge. Delamination and spalling can reduce the cross-section of the concrete, in turn reducing the capacity of the bridge. Corrosion of the steel reinforcement also can reduce the cross-section of the rebars, and this can reduce the capacity of the bridge. Bone degradation between the concrete and the steel reinforcement can cause the reduction in the tensile resistance of the bridge. So, inspection is a major part to obtain the present conditions of the bridge. Based on the present condition of the bridge, the capacity is calculated. After getting the capacity, these 3 methods can be used for load rating of the bridges. So, inspection is usually accomplished by manual visual inspection. However, this method is time consuming and expensive. In the areas where it is inaccessible, it poses a risk to the safety of the inspectors. Moreover, this method is subjective to the skills and experience of the inspectors. So, the condition assessment of the same bridge can vary from one inspector to another. In order to eliminate these limitations, inspection of the structures can be automated. With the development of unmanned aerial vehicle technologies and with the development of image processing methods and computer vision methods, UAVs or drones and deep learning techniques have been used in the inspection for civil infrastructures. This method is supposed to be efficient and cost effective. It will lower the danger of workplace accidents, and the decision made on the present condition of the bridge will be objective and rational. The major objective of the study is to develop an automated inspection method to assess the condition of the bridge using UAV and deep learning techniques. A UAV or a drone will be used to collect the images of the bridge. Deep learning technique will be used to process these images and determine the condition of the bridge. This is a preliminary study, so we are just going to talk about the cracks in this study. The first objective of the study is to develop a deep learning model, a convolutional neural network model, and implement this model for crack detection. To determine the propagation of the crack, to determine the condition of the crack, we will develop a multiclass CNN model to classify the images based on the crack depth. Thirdly, we will develop an integrated CNN model with a regression model for concrete crack depth prediction. The prediction of the crack will help us to make a decision on carrying out further assessment to check corrosion or bone degradation. The first objective is development and implementation of a CNN model for crack detection. The CNN model consists of an input layer, a CNN architecture or a CNN model, and an output layer. In the input layer, images of the concrete surfaces will be input to the CNN model. The CNN model has convolutional layer and pooling layer that will extract the features from the images. The CNN model works like a human brain, so it will identify the difference in the features such as brightness, the sharpness in intensity, the presence of the lines between the images having cracks and having no cracks. So after the feature extraction from convolutional and pooling layer, fully connected layer and output layer will be used for classification. The output layer will assign the input images to their respective levels as undamaged or cracked. The performance of the CNN model will be evaluated using a confusion matrix. So for the input, we used a total of 40,000 images that were collected from the ImageNet database. These images are classified and labeled into two separate folders. So one will be undamaged, which contains the images of concrete surface without any cracks, and the second will be labeled as crack. These images will be the images of the concrete surface with cracks. So for the evaluation of the CNN model, these 40,000 images will be used. Out of the 40,000 images, 20,000 images will be labeled and separated to undamaged. 20,000 images will be separated to crack. 70% of the undamaged images will be used for training and 30% will be used for testing. So these images will be input into the CNN model. The CNN, after the execution of the CNN model, we got an accuracy of 99.9% in classifying the images to their respective labels as undamaged and cracked. So in this part of the study, we developed a CNN model with an accuracy of 99% to classify the images and detect the presence of the crack. So after the development of the CNN model, we are going to implement the CNN model in our lab, in the images that we collected from the lab. So in our lab, we had a precast RC slab. We tested the slab. The damage condition of the slab can be seen in the middle figure. We used a drone to take a video of the damages in the slab. So an algorithm was developed to extract the images from the videos. We want to check the reliability of the CNN model we developed. So the images that were extracted from the video were manually separated into two folders, undamaged and cracked. These folders were input into the CNN model. The CNN model gave an accuracy of 93.7% in classifying these images to the undamaged and cracked. So from this, we can see that the model that we developed previously is reliable. in classifying the images that it had not seen before. So the second objective of the study is to develop a multi-class CNN model to classify the images based on crack depth. So similar to the previous study, in this study we have image dataset for the input. In this study, the image dataset are divided into 3 folders. The 3 folders has images with varying depths. So these depths will be separated into 3 zones: Zone 1, Zone 2 and Zone 3. The images will be input into the multi-class CNN model. Convolutional layer and pooling layer will extract the features. Fully connected layer and output layer will classify these images to 3 zones. The performance of this model will be evaluated using a confusion matrix. So to generate the image database, we have a precast slab, we have the damages in the slab. We use the drone to take images of the damage of the cracks in the slab. We have 15 images with large cracks. Since this is a preliminary study, we just want to focus on single crack in a single image. So we cropped the original image and got larger database. Data augmentation was used to generate a large amount of database. So the image dataset was classified into 3 zones. Zone 1 with a depth range less than 1 centimeter. Zone 2 with a depth range 1 centimeter to 2 centimeter. And Zone 3 with the depth more than 2 centimeter. For the evaluation of the multi-class CNN model, these images that were separated into 3 zones were fed into the multi-class CNN model. 70% of the images were used for training and 30% of the data was used for testing. So in the confusion matrix, we can see we have an accuracy of 87.9% in classifying the images to their respective zones, Zone 1, Zone 2 and Zone 3. So from this, we developed a multi-class CNN model to classify the images based on their depth. Thirdly, we developed an integrated CNN model with a regression model as a classifier for concrete crack depth prediction. An integrated CNN model is a model consisting of a CNN model and a regression model as a classifier. In this study, we have the image dataset. The images have their depth linked to the images. These images will be input into the CNN model. The CNN model will extract the features from these images. These features were input into the regression model for crack depth prediction. The performance of the model was evaluated in terms of I-square value. So this is the image dataset. We have the images of the crack in the slab. Thus, the images have their depths known. So in the table you can see 1 is 1.1 means the crack number 1 has a depth of 1.1 centimeter. So in this way we have the large data set for concrete crack depths. For the evaluation of the regression model, we have the cracks. We know the depth of the crack, which are linked to the images. These images were cropped because we want to just focus on a single crack in a single image. These images were input into the CNN model. The features from CNN model were input into the regression model with their depth, and we plotted the actual and predicted values, and we got a good correlation between the actual and predicted values from the model. So in this study, we developed an integrated CNN model to predict the depth of the crack in the images. So in conclusion, we developed a CNN model which was accurate and reliable in detecting the presence of the crack. We classified the images for damage severity based on the depth of the crack using a multi-class CNN, and we developed an integrated CNN model for the prediction of the depth of the cracks. So these are the future works. This is a preliminary study, so we just focus on the cracks and the presence of the crack and the depth of the crack. So Later, we want to develop a deep learning model which to obtain the geometrical information of the cracks such as width, length and orientation. We want to determine what kind of crack it is it shear crack or flexural crack. Secondly, we want to develop a deep learning model that can give us the information on loss of cross-section of the structure. So I want to thank my professor, Dr. Paul Ziehl at University of South Carolina, and I want to thank ACI for giving me this opportunity to present here. Thank you.